Good morning, everybody. Welcome to the first session on I/O. We have 3 papers, and the first speaker is Yuan, who is going to talk about driving the drivers.
Thanks, Victor. Thanks for the organizers. Hello, everyone. This is Zhe Yuan from Zhejiang University. I used to graduate from Toronto, and this is called the paper with Yanyu Chen and Yao Luo, both from University of Toronto. So recent years, we have witnessed the rapid acceleration of the algorithmic technology. And we observed the assignment algorithms It looks like this also looks like the assignment algorithm when a lot of people come to the room. It sometimes is assigned by the algorithm. So this assignment algorithm is a preferential algorithm or bonuses for the competing many trips, which may result in some flexibility penalty. For instance, in the ride-hailing platforms, like in Uber, in China, we have DD. So when we interview with the drivers, all the drivers know that when you do some strategic behavior, for instance, when you operate in several very important hours, then you will be assigned more orders. Sorry, I had something wrong with my, so, and the drivers, they also share some, for instance, WeChat groups, and they always communicate on how to strategic behavior in order to get more orders assigned by the algorithm. So in this paper, we try to provide the first empirical study of the preferential algorithm and its impact on the worker behavior and the welfare. And we are going to address 2 empirical questions. The first one is, would assignment algorithm favor some workers? If yes, and why and how? And the second, how would the platform revenue and the driver surplus change if the platform cannot use preferential algorithms? And a quick preview of the findings. Our reduced form evidence shows that the preferential assignment algorithm is based on the driver's hourly work schedule. The drivers who are favored by the algorithm can earn 8% more hourly than the other drivers. And then we construct a structure model and find that the platform revenue will decrease by 12% without the preferential algorithm assignment. And the drivers, especially the young and the local ones, will have a higher surplus without the preferential algorithm. And our study contributes to several streams of literature on how the algorithm will affect the market outcomes, the labor literature on the compensation and work flexibility, and the literature on taxi and the ride-hailing. And we also adopt several I/O techniques, so we are also related to this literature. Let me first introduce what is the institutional background and what is the preferential algorithm we talk about. Okay, so take ride-hailing industry for example. Suppose we have one rider who want to travel from the origin O to the destination D, and the platform have 2 types of drivers. For simplicity, we assume that we have a high type H and the low type L. And supposing that these 2 drivers, H and L, they are the same distance from the origin O, then a preferential algorithm will assign this order to type H driver because this driver is preferred by the algorithm. And suppose we have 2 drivers, H and L. However, the H type driver may be farther away from the origin. compared to the L-type driver, it is possible that the preferential algorithm will also assign the order to the type H driver instead of type L driver, because type H driver is preferred by the platform algorithm. And this preferential algorithm, sometimes it is explicit, sometimes it is implicit. Here's the example. This is the score, driver score displayed on one of the platform we study. And it shows that this driver is better than 66% of drivers in the same city. And it explicitly shows that the higher the score, the higher priority you will get in order assignment. We have a theoretical motivation, but due to time limitation, I'm not going to discuss them in detail. And let me go to the reduced form evidence directly. So the data we use is all the completed transactions in December 2018 of a major city in Asia. And in the data set, we can observe the departure, the destination, and the distance of a trip, and the time spent picking up and transporting passengers, and the price paid by the driver. And we also observe the driver's attributes, such as the age, their gender, and their birth location. And this ride-hailing industry is highly concentrated in China back in 2018. For instance, the platform X is dominating this market in the year 2020. And it serves around 500 million users. And also it manages over 10 million drivers. So it consists of over 90% of the market share in the focal city we study. And for the summary statistics, we report the driver hour level summary statistic here. The origin data set is order level, but then we find a way to convert it to a driver hour level observation. On average, the driver will earn about 50 RMB, and for each hour, about half of the time, which is 30 minutes, the driver is earning money, meaning that they are serving passengers. And they also need to spend about 10 minutes in picking up the passengers. And in the remaining about 19 minutes, they are idling and they are waiting for the platform to assign order to the drivers. And on average, the driver can serve two orders per hour and travel for about 14 kilometers. So we have about 4 million observations in our data set. So we are interested in who will earn a higher hourly wage. Then we try to explore how does the hourly wage of a driver depending on their working schedule of the drivers. And we find that two very important factors in determining the hourly wage of the driver. The first one is the number of hours they work in an hour. And the second one is the percentage of incentivized hours for the drivers. So it means that the longer you work on the platform, you will be assigned for more orders or better orders, and you can earn more money. And when you work more in the incentivized hours, you will also be able to get more orders and high quality orders. So you will earn more money based on these orders. And the incentivized hours we define as the time as hours in the middle day for instance, between 10 a.m. to 4 p.m. and in the evening. So we based on this definition, we separate the drivers into two groups. And the first group, we call it high score drivers. So these are the drivers who commit to work for at least 2 consecutive hours during these incentivized hours. So for instance, for the drivers who work from who are willing to work from 10 a.m. to 12 p.m., this as one type of the high score driver. We call it S1. And there are other types. For instance, S2 the S2 type will be those who are willing to operate between 11 a.m. to 1 p.m. So we have a total of 16 different types of high score drivers. And the rest of the drivers, meaning that these drivers who are not able to supply their labor in 2 consecutive hours in the incentivized hours, we call it S0 or the low score drivers. Yes. Yeah. So this is based on our based on our exploration of the data. We use the machine learning algorithm to so we feed all the data to the algorithm, and we ask the algorithm to show us what are the key determinants of the wage differential, and these are and the algorithm show that when people work more in the middle day and in the evening, then they are going to have a higher wage. So we construct our definition of the high score drivers based on this finding. Oh, yes. So we are not saying, sorry, I should clarify that. So this means that they are committed to work at least during these 2 hours. So they are also flexible to choose to work in the other hours. So recall that, so we are studying a gig economy. Gig economy means that everyone can work whenever they want. However, with the preferential algorithm requires that you have to work in some consecutive hours. So this will restrict your flexibility. Yeah, this is what the thing we are going to study. Yeah, yeah. Thanks for raising the question. I'm going to talk about that in maybe 3 slides, but I can give you a quick preview. The high quality customer means that the customer who do not cancel their order after matching. Yeah. Please. So the drivers, some of them may know these incentive hours because they play with the algorithm all the time, and they have their WeChat group which can communicate based on this is how I work for last month, and this I get more orders for this month. Yeah, they are always talking about that. Yeah. And this is also consistent with our anecdotal evidence or our interviews with the drivers. Okay, then we compare the performance between the high score drivers with the low score drivers, and we find that for the high score drivers, most of them they are non-local, and for the low this is also consistent with our interview. So the non-local, they work harder. So they work on longer hours here. And Yeah, and then they earn more money because the non-local, they work in this industry to as a way of living, but the local people sometimes they just earn some extra cash for their spending. Then we compare the wage differential between the high score drivers and the low score drivers. And we run a regression based a dependent variable will be the hourly wage, and the independent variable will be the high score or is a dummy variable indicating whether the driver is a high score driver or not. And we find that this regardless of the control variable we include, we have around 4 RMB wage differential between the high score and the low score drivers. And remember, we have 50 RMB on average for the drivers. So this 4 RMB is equivalent to 8% of the wage gap. And this wage gap is consistent across all the hours per day when we display the high score driver in the blue line and the low score driver in the red line. So we are going to explore the driving force of the wage differential. So why, how does the algorithm do so that the high score driver can earn more money than the low score driver? And we consider 5 different variables. The first one will be the number of orders. And we find that the high score driver can serve 7% more orders compared to the low score driver. And in terms of the quality of the rider, we measure it by the cancellation rate. We find that there is a 3% lower cancellation rate for the rider who are matched with the high score driver. So it says that this shows that it's higher quality drivers, higher quality riders. And the high score drivers will travel for longer distance. They serve more time in they spend more time in serving passengers instead of idling and waiting for the orders. So that's the driving force of the wage differential. To summarize, the high score drivers can get assigned more rides, and they spend less time idling, and they're assigned to drivers with a lower cancellation rate. And there are several competing hypotheses in the literature. The first one is that the drivers may strategically choose where to work, and the drivers may also strategically cancel their orders that are maybe too close or too difficult to travel to. And the drivers may travel fast, or they may know the route better. So we look at the service areas, and we don't find a very substantial difference between these two type of drivers. And then we try to show the wage differential controlling for final grades in terms of the day hour 15 minutes time interval, and we separate the city into final grade, and we also we all find that our results are quite robust to different specifications. And then we show that the driver's cancellation rate is actually lower for the high score drivers compared to the low score drivers, because the drivers they all know that if you cancel the order for a lot, then you will get a penalty by the algorithm. So the high score driver, they don't want to cancel orders. So they are not strategically selecting orders. They just finish all the orders assigned by the algorithm. And in terms of of the driving speed. The high score drivers, they drive 0.5% faster than the low type drivers. However, this 0.5% difference cannot explain the 8% weight gap between the high score driver and the low score driver. Okay. Questions? Okay, then because in this paper, we want to study what will happen when the platform use a fair algorithm, which means that there is no preferential algorithm and everyone get a random assignment of the orders. Then we need a model of dynamic labor supply. So here's the model. In step 1, the platform will announce the price. They will announce a price P, which is the rider's fare by the hour. And then based on the rider's fare, we have the demand for the ride hailing for this industry, which is a function D. Then we can get the total fare paid by the rider. And we assume the platform will assign a fraction, the S fraction, of the trip to the high score driver. So this is a strategic variable decided by the platform. And there are NH number of the high score drivers in this market. And we assume 80% of the wage of the revenue will go to the driver. This variable is calculated based on the annual report of the platform. So so we will calculate the high score wage rate based on this formula. And similarly, we can also obtain the low score wage rate. And each driver, they are going to choose a work schedule in 2 steps. A work schedule of type J, they are going to first select a work schedule of type J. They can select to be, for instance, S1, which means that they have to work 2 consecutive hours between 10 a.m. to 12 p.m. So they have to work in these 2 hours, meaning that they are going to, for each driver, they are going to solve a optimization problem, a constraint optimization problem. And the constraint will be that they have to operate in these 2 hours. Or they can choose to be flexible, which is S0, so they can choose to work whenever they want. And then they are going to decide their exact schedule. And when they decide their exact schedule, they are going to have a constraint of the work schedule J, which is in the first step. And because in this market, we have this is a 2-sided market. So we have a passenger demand, which is measured by the earning time. We use a very simple constant elastic demand function to represent the demand in this market. And in terms of the driver's dynamic labor supply, this is the wage rate we calculated. And then we have the platform which match the driver and the drivers and the passengers. And we assume that in order for the market to clear, the supply should be larger than the demand. And the driver's problem, for individual drivers, they are going to decide a finite horizon dynamic decision problem. So we model the driver's work in 1 day, so 24 hours. So they have to decide whether they want to work in each hour. So there are 24 different decisions they are going to make. When they choose to work, they can collect in one specific hour T, they are going to collect the wage T in this hour. And when they choose not to work, they are going to obtain their outside option. And we also allow for unobserved heterogeneity in this outside option. In order to introduce the time dependence within this model, we introduce a warm-up cost kappa, which is a transition cost from not working to working. So you have to, for instance, you have to go downstairs and warm up your car, and these are captured by this cost. And we can aggregate the labor supply by the hour and solve the model. Okay. Okay, the results. So we use the conditional choice-based estimate of the to estimate the outside option value and the kappa. The main parameters we care about are the hourly reservation value, the unobserved heterogeneity, the warm-up cost, and the normalization term. And we use the method of simulated moments to estimate all the parameters. So we can observe the condition choice probability from the data, and then we select the parameter that that can match our match our model prediction with the data. This is the condition choice probability of working that we simulated from data. So for the let's look at this curve. So these are the low performing or low score drivers who work in the past hour. They are more likely to work in the next hour. And if you are not working in the past hour, then you are less likely to work in the next hour. So this also shows the dependency across time. And here's our model fitness, which is not bad, even that we only have about 20 less than 30 parameters in our model. And this is the estimated reservation value. Okay. And we also estimate the unobserved heterogeneity, but due to time limitation, I don't want to go to the details here. Okay. So the last simulation we do is that we are interested in what will happen if we eliminate the preferential algorithm. So we use a fair pay across the platform. So the non-preferential algorithm means that we have a random assignment of the orders. We don't have an S variable now. So all the drivers, they can be randomly assigned of the orders. So the drivers, they don't need to commit to any hours. So given the new hourly wage, the driver will solve a new dynamic discrete choice model. So who will gain and who will lose? We find that 10% of the drivers who used to commit to some specific working schedule will switch to the flexible schedules. And this will reduce their total work hours. So these are the workers who are forced to work more because of the preferential algorithm. They want to get a higher wage, so they have to work more, they have to stay longer. Now, we don't have the workings, now we have the random assignment, so they don't need to work more so they don't need to work more, and they can earn yeah, they can earn okay, sorry. The platform revenue will decrease by 12% without a fair adjustment. And we show that the right fare will increase by around 7%. When we consider the fare adjustment. And there is a 4% surplus gain for the drivers who will switch to the flexible schedules. So these are the consequences for allowing for a more flexible wage, to allow for the random assignment and fair pay. Okay, to conclude, we document the preferential algorithm based on the hourly work schedule, and the drivers favored by the algorithm can earn 8% more hourly than the other drivers. And then we construct and estimate a two-sided market model with dynamic label supply. We show that the platform revenue will decrease by 12%, and the total surplus will decrease by 8% if we eliminate the preferential algorithm, but when we fix the price. And without the preferential algorithm, there will be an additional 10% of the drivers will switch to a flexible schedule, and young female and the local drivers will benefit more from the non-preferential algorithm. These are the results from the unobserved heterogeneity estimation, but I don't have time to show that here. Thank you.
Hello, is it on? Let's get started, given the time constraint. So thank you very much for putting our paper in these sections. This is a joint work with Henry Hussain at U of Toronto, Shravan Tarani at UT Dallas, and Travis Zhao at McGill University. And in this paper, we're going to be studying how do people update their beliefs, how do people learn. It's going to be a study that uses experimental data that we collected from the U of Toronto experimental lab. So some motivations, why do we study this question? Now, consumer learning or Bayesian learning model is something that a lot of people use in the empirical structural estimation literature. And it's very popular. But why do people impose these type of this kind of structures when we study learning problems? Is it because we have a lot of evidence that support people are Bayesian? Not really. Well, the main problem or the main reason why people use these type of models in structural estimation is because we oftentimes only are able to observe choice data. We don't observe beliefs data directly. And so what we do is we try to use review preferences, and based on choices, we try to reverse engineer to learn something about people's beliefs, about preferences. This is really the reasons why that the literature try to take this Bayesian learning approach, impose structure, be a more parsimonious, so that we are able to, in a more disciplined way, to apply review preferences and learn something about how people learn. But it's not really because we have a lot of evidence to support that people are Bayesian. And I don't have to tell you, if we misspecify the updating rules when we estimate these type of models, we could naturally need some misleading problems, misleading implications. Parameters could be biased. The counterfactual experiments, counterfactual predictions could be biased. So here we are. So we try to attack this problem by asking the following questions. How do people update their beliefs, distributions? And we will want to impose Bayesian structure. How do people differ from each other? Right? So in the empirical structural learning literature, because of this problem that we don't observe belief data, we don't want to be too flexible. Right? In addition to imposing Bayesian updating rules, oftentimes the literature also assumes consumers' learning behavior is homogeneous. Okay? Even that kind of homogeneous learning rules could lead to heterogeneous behavior because the signals are different from each other. So that can oftentimes lead to different beliefs over time. However, if learning moves are different from heterogeneous in the populations. That can be something have a lot of implications as well. And another question we want to ask is it possible that people actually change their belief updating rules over time? Not only about their heterogeneous across individuals, maybe the way they update beliefs, right, could also be dynamically evolving over time. It could be initially underreact relative to the Bayesian counterpart, but over time they become, sort of correct that kind of behavior, and even become overreact later on. So that's something we want to see if we can learn something about. So how do we attack these problems? We're going to be collecting data, belief distribution data from the lab, and we will be using an incentive-compatible way to elicit beliefs. That's something that my co-author Tenzin Hussain has developed binarized scoring rules that they figured out a way to make payments to the subjects so that they will have incentive to truthfully review their beliefs. So we're going to use that method to help us collect data on belief distributions. And with the belief data, there are a lot of things that can be done in a very straightforward way. We can allow for flexible specifications of the updating rules. We can allow for heterogeneity in the updating rules. And so that's how we're going to address question 2 and 3, in fact. We can even allow the updating rules to be, time specific or, signal specific. So that's something some evidence. In the interest of time, come right into the experimental design. The way we sort of think about these lab experiments is to ask subjects to imagine that you will just come to a new neighborhood, right? And you have very little ideas about, you need to buy a house, you have very little ideas about the housing market conditions. And you may go around and ask some real estate agents, right, to give you some ideas about, I'm interested in this house. How much do you think it's worth? And your real estate agent will give you a number. And then based on the number, you might update your belief. So that's how this game is played. Each subject, they have a house, they try to evaluate this true price. And there's 7 periods. In each period, a subject will consult a different expert about the estimate about the selling price or how much this house is worth. And these 7 expert estimates, you can think of it as a signal. It is normally distributed around the true value of the house. So there's a true value of the house and the signal, the estimate, is normally distributed around this S value. And it's an idea across these experts. Okay? So this is a very standard setup, very similar to what a lot of people do when they apply Bayesian learnings to choice data, including Erden Keen and some of my works that I've done in the past. So after each period, after you receive this estimate, we will ask the subjects to come up with a new guess about the best guess about the price of the house. And that will represent the posterior mean. And we will also ask them about how uncertain or how certain they are about this guess. Right? And this capture the ideas of posterior variance. So the initial prior, we're going to give it to them as well. We're going to be moderate in such a way that it is a normal initial prior. And if you have normal signals, if it is a Bayesian, have conjugate prior structures, then we'll also need to posterior distributions to be normal. Now that we're going to be agnostic about it, but what we're interested in is this posterior mean and posterior variance, how that evolves over time after you receive each signal. And the good thing is that we know exactly what a signal is. In this case, we know exactly what the number is given to the subjects. And now at the very end of each round, at the end of the 7th period, then the actual selling price will be revealed to the individual. That's the basic idea of experiment. And I'm going to tell you a little bit more about. Let's see. So this picture just basically captures what I told you. They start with initial prior. They receive an estimate from one of the experts. Then we list their posterior beliefs, U1 and GH, HU1, H1, and then you keep going until period 7. I want to say a few words about these ideas of certainty level. And although we did try to make sure the subjects that we recruit, they are University of Toronto students, they have at least taken a course in statistics, and we even try to give them a comparison test to make sure that they understand basic concept of variance, means, these kind of things. But when we try to ask them to report their posterior variance, we kind of get something very impossible. And so we don't know exactly why, but Andrew is very experienced in collecting experimental data, and he's not surprised to see that, just because naturally when we choose things, right? When we make decisions, it's not like we keep asking ourselves, hey, how certain am I? What is my variance about my belief, my best guess about the price? We don't operate this way, at least not consciously. So the kind of variance data that we got, we just don't even think it's very possible. So we decided to sort of twist things a little bit. Instead of asking the subjects to report variance directly, we come up with a way that we hope is more intuitive, that's more natural for the consumers, for the subjects to think about. We ask them how certain you are about your belief, your best guess. And what we ask them is that, hey, what do you think is the probability, the chances that your best guess, okay, the true values of the house, or within the plus and minus 25 is small bandwidth around your best guess. And now you can show that this certainty level concept has a one-to-one mapping between the variance term and this H. And so in the experiment, we're going to ask them about H, ask them to report H. But then we can always just convert it back to variance. Right? What else do I want to show you? So this is the binarized scoring rules. And just very quickly, what it basically does is instead of make the payment as a function of the payoffs, make a function of guess by itself, we make it as a function of the probability that that you will receive an award. And it turns out, when you just twist it this way, it is incentive compatible, and it is invariant of individual risk preferences as well. And so we use this method. So there's a beliefs. This is something, not the invention of this particular paper, so I'm going to just skip it. This is to you during the break. And as I said, the exact experiment procedures is that first we'll give a comprehensive test to make sure that the students have some ideas about what the statistical concepts are. Run the videos, play the videos, show the instructions, and also we run the experiments in the way that we first ask the subjects play with 4 practice house. So these 4 practice house is something that we don't actually use it in our estimation. It's just something that to make sure that the subjects know the rule of the game before we get to these pay houses, where we're going to use the information that we collected for estimation. And then at the end of all the rounds, individual will be paid for what they report. And Now, the way we manipulate our parameters is as follows. So each individual will be given them 4 different initial prior beliefs. So they will be these numbers here: 660, 750, 830, and 940. But essentially, actually multiply 1,000 to get to a more realistic price of the house. And the standard deviation of the initial prior belief is 110. That can go to a certain level, about 18%. And now for the signals from the expert, we're going to consider 2 different levels. One is we call it high precision, one is low precisions. So that basically we're manipulating how noisy the information signal is from the expert. And so we're going to choose 4 houses that were assigned with high precision signals, and then the other 4 with the low precision signals. And for each set of these 4 houses, they will also be sort of randomly assigned one of the initial prior. So that will make sure that when we collect the data, it is coming from a set of parameters with very rich variations. So it will be with some variations that start from the initial priors and also vary according to how noisy the signals are. And in total, we have recruited 104 subjects, and 40 of them are males, and the average age is 20.5. So this is just notations. I don't think I need to do that. So how do we exactly specify our model when we take it to the data? And now, if you're familiar with Bayesian learning, these kind of formulas is something you will be very familiar with. But basically, what it basically says is the beliefs, the mean beliefs, or possible beliefs, GT, is a function of your last GT minus 1. Plus, kind of a weighted measures depending on the difference between the signal and your previous period. So that's the sort of new informations. And how much weight you put on that new information, ET minus GT minus 1, that depending on your prior beliefs up to that point. Okay? If your prior beliefs up to that point, if you're Bayesian, you have a very precise belief, and you put less weight on that new information. So it's easy to manipulate these formulas such that you can just write the difference between GT and GT minus 1, the mean beliefs from this period and last period, is a function of beta t times ET minus GT minus 1, the new signals minus your previous period beliefs. And now with the data about beliefs, GT minus 1, right, and ET is something that we actually observe. We can actually estimate beta t here. So normally when you impose Bayesian estimation, beta t will be predicted by the Bayesian model. And now we're going to just relax that assumption. We're going to estimate this beta t. And we're going to allow the beta t to be a function of how precise the signals are. And now, the certainty level equations, we're going to specify in a way that is also quite very similar to the one I just showed you for the posterior mean equations. Now then we estimate a model. Now we have 104 subjects, right? And each subject's weight 8,000. And each house lasts for 7 rounds. So in total, we have 4,824 observations. And we're going to allow for consumer heterogeneity. We use finite mixtures. And we tried 6 different types. And we found that the model with 5 types is able to explain the data the best. And in terms of the types probability, type 1 is the largest with about 40%. Type 2 is 30%, and type 3 is 14%. Type 4 is 10%. Type 5 is the smallest. It's about 4.8%. One first things that we can learn from this result is that subjects are heterogeneous in their updating rules. So unlike the standard literatures, where oftentimes they assume subjects are homogeneous. From an empirical researcher's point of view, that may not be surprising, but we see that there it's like 5 types that are possible. I think that's something also worth noting. And now here, what we do is we basically plot the result, to visualize the result. And what we do is on the left, it is the reported best guess. I'm sorry that we have that green bar there to block what we actually have. What we are actually plotting is your best guess minus the true values. Absolute guess error. And on the right, these 2 panels, one is for low precision, one is high precisions. That's plotting how the certainty level changes over. So one thing you can see is that the blue one is predicted by the Bayesian model. It's nice and concave, but when you look at the data and how people actually update their posterior variance or certainty levels, it turns out that it is quite a lot lower than what the Bayesian model would predict. So they actually have a lot less confidence about their guess. And when you look at the best guess errors, there are actually some of them quite close to the Bayesian, like type 1 high precisions and also low precisions. You will see the orange line, which is predicted by the model, and the blue line is the Bayesian predictions. They're actually reasonably close, even for type 2 as well. And so that's actually kind of surprising. A lot of people would think, oh, people cannot be Bayesian. But when you look at the empirical result from this set of lab data, for the mean updating process, is of course they're deviated, but it's not that bad compared to what they. So we also plot the effect of the signals on the posterior mean and the certainty level. That is the beta term and also the alpha terms that I showed you earlier. So here you will see that sort of like you can see how to deviate from the Bayesian model from a different way. And I think one thing I would notice is that for the certainty level, it will start off, deviate quite a bit, and then later it actually converges. And so, however, even it converges later, it doesn't change the fact that you started off pretty far away from the Bayesian model, so then you sort of stay far away from it in terms of the absolute certainty level. And so let me just generalize the result a little bit. So the second result that we think we can generalize from our finding is that subjects' beliefs updating rules, regardless of types, they deviated from Bayesian updating. But relatively speaking, we see that the posterior certainty level deviates much more. And people tend to have a lot less confidence about the guess than what the Bayesian model thinks. About the posterior mean updating rules, we actually see that the majority of the subjects, 80% of them, with the mean beliefs updating rules roughly consistent with Bayesian. But there are 20% of them significantly deviate from it. And with respect to the certainty level updating rules or the posterior variance updating rules, what we see is that the majority of the subjects show very degree of underreaction. Right? And so in general, they improve their certainty level much slower than what the Bayesian model would predict. But as they receive more signals, then they become more reactive to the new information when they update their variance. And they even converges to the Bayesian counterpart. However, because they start off far away, their posterior certainty level remains far away, even up to period set relative to the Bayesian. Now, finally, we also ask the questions, what if people receive a surprising signal? So even though the signal is normally distributed around the true values of the house, occasionally you might get a draw that is very far away from the true value of the house. Right? And we ask the questions, hey, given that we actually know the signals, right, we can sort of tell which signal is more surprising. And we can ask the questions in the model, we can allow for some flexibility there and see how people react surprisingly. And so what we do is simply we just add a dummy variable and we decide that, if the signal that we receive is at least 1.5 times the standard deviation away from your previous best guess, your current best guess, we're going to call that as a surprising signal. And so these dummy variables, indicator functions, interact with the gamma g's, interacted with the different species, and your best guess. That will be the parameters that will help us to capture how people react to the surprising signal. And I think I'm even out of time by now. But very quickly, I'm going to just point it out that it's the gamma g that we're interested in, and this is the posterior mean equations. And what you see is that when you come with the surprising signals, some people become underreacted. But there's one type of individual, type 4, they actually overreact. I don't know why they would do that. But for the posterior certainty levels, they're very consistent. If you look at the gamma h, the interaction term, what you will see is that when people receive a surprising signal, they become a lot less certain about their belief. They will suddenly just lose a lot of confidence. And that's something that's very different from a Bayesian model would predict. A Bayesian model would predict, doesn't matter what the signal is, right? When you update your posterior variance, you always, with the more signals you receive, the more precise, the more confidence you're going to have. Right? And now, but you think about the real world, that perhaps it's not surprising. If we see something suddenly very different from what you believe, you may wonder, what I learned before, is it valid? Right? Maybe there's some fundamental change in the distributions. Something to investigate. So this is what we got. And I'm going to conclude. I still have a couple minutes. Okay, now let me just point out that for the surprising signals, just want to give you some idea. Given the cutoff that we pick, we have about 19.5% of the signals that are surprising. Okay, so there's still, I think, good enough variations to help us to identify the surprising signal results. And so I am going to just conclude, right? Given I have 3 minutes left. And so the main finding is that, well, not surprisingly, perhaps, that individuals don't update beliefs like perfect Bayesian. And we identified 5 different types, and they're evolving over time as well. So I think this is what's new. There are certainly some experimental literatures, some experimental papers that show evidence that people are not Bayesian, but those experiments usually is one shot. They just let people think, here's your beliefs, this is a signal. And then after that, they try to check whether what you update is Bayesian or not. They don't look at the dynamic. And so in this environment that we have, we follow individuals 7 periods. And so that allows us to learn about not just like initially how you react, but later on how you might change your updating rules. And that allows us to learn more insight. So beyond the static types, we see that in the existing literature, people will usually just classify people are, oh, you're conservative, or you're overreactors, right? And the type is kind of like fixed, at least implicitly, kind of what the paper implies is. But what we find is that your types could actually change over time, right? So people could evolve from underreact to become, more or less Bayesian, and then become overreact. That's actually possible in our results. That's what we found. And we also found that posterior certainty level, posterior variance, does deviate from the Bayesian benchmark much more than what the posterior mean would do. And for the surprise effect, when people face surprising signals, order certainty level, they uniformly will lose confidence a lot quicker. And finally, some limitations. Of course, this is lab experiments data. We don't, whether our result extend to the real world is something, to be seen in the future research. And I also want to say that what we are doing is a bit different from the structural estimation in the learning models where we just look at choice data. Here, we actually just look at belief data. And so there's still very big questions about how people link the beliefs to choices. Right? That's something we hope to address in our future research. So that's all I want to share. Thank you.
Okay. So thank you for this great talks. I actually combined this mental approach. So today I'm going to talk about cross-product compatibility, locking market power interface. So the starting point of this talk is that just in the last year, both the DOJ and the started scrutinize Apple for limiting the compatibility of products, limiting the compatibility across its products. Now, cross-product compatibility is a set of features that allow consumers to connect their product. So the simple example is that when you have compatible smartphone and laptop, you can copy paste across them. Just press Control-C in one device and Control-V in your complementary device as if they were one. Now, on one hand, this is great news for consumers since it adds on their utility from products. But on the other, firms use this compatibility to attract and tie consumers to their brand. And to see that, we can observe an internal email from Steve Jobs to senior managers where he says, tie all of our products together so we further lock customers into our ecosystem. This clearly raises an empirical question, which take us to the message questions. So in context of smartphones and laptops in the US market, first I asked, what is the welfare effect of a regulator forcing firms to open their ecosystem, so cross-brand compatibility? Second, what is the welfare effect of a cross-market merger, Samsung and HP, which are Apple's main competitor in the smartphone and laptop market, respectively? To motivate the second question, note that if we ignore the role of compatibility, as the DOJ did in the previous case of Motorola and Lenovo merger, then the second question is no longer the second question is moot since there will be no effect on demand because of increase in compatibility of the joint merged firm. Now, for both of these questions, the welfare effect is ambiguous because on one hand, there is an expansion in compatible product variety, but on the other, prices may increase. So in order to answer these two questions, first, I'll recover the causal effect of compatibility on smartphone demand using an incentivized experiment. And in a few slides, I'll explain why we have to use an experiment rather than just market data. Just for now, I'll mention the results. I find that compatibility with laptops increases the willingness to pay for a smartphone by 9% of the smartphone price. Then I use this result to construct smartphone demand model, which incorporate compatibility characteristics with laptops, which is taken as given. This allowed me to examine the two questions that I just mentioned. Quickly going over the contribution. So first, this paper provides a methodology improvement. In an overview of the IO literature, Pecos says that IO structural models have difficulty distinguishing between correlation in taste and causal factors that lead to similar actions. In our context, even if we perfectly observe smartphone and laptop purchases, we cannot conclude whether this is due to compatibility or other effects. The reason that we cannot use market data is because smartphone and laptop are not purchased at the same time. Either they're purchased frequently and their product characteristics change over time. Because of that, not use any off-the-shelf methodology, such as RShove, who provides suggestive spatial evidence when examining cross-market merger of soda and sperm, but we must design an experiment to recover the causal effect of compatibility on smartphone demand. Second contribution is to the literature on product compatibility. So until now, the literature has concentrated on the compatibility between add-on products, such as hardware and software, camera and lenses, and charging solutions. This paper revealed the role of compatibility across standalone products, and which until now was attributed to other things such as brand preference and loyalty to brands. By that, it showed that the dependency of technology markets and contribute to the literature on quality products such as Eisenberg, C market, and Feng and Yang, who examined the smart market. And it shows a welfare trade-off arising from closed ecosystem, as we see the back. Second, it shows how firms exacerbate their power across ostensibly independent markets. So now I'm gonna quickly go over the experiment. I'll not show you our experiment, just the outline. Forever, and now we'll get to the. So data which I collected show that there is a positive correlation between smartphone and laptop brand purchases. The question is whether this is due to compatibility. Now, there are two reasons why we should suspect this is not due to compatibility. First, smartphone prices are independent of compatibility. So it doesn't matter what laptop you do versus smartphone, they're exactly the same price as smartphone. And second, the literature provides no evidence that compatibility affects the decision-making across standalone products, only for add-on products. Because of that, the goal of the experiment is disentangling the compatibility. So as I said, now just go over the outline of the experiment, and then we'll move to the study. So this first step, I asked participants for the willingness to pay for a smartphone. Then I parachute over them a laptop, and I tell them, conditional on the laptop, Steve, what is your willingness to pay for a smartphone? Because I exogenously provide the laptop, I can conclude causality between compatibility and the willingness to pay for smartphone. I do that by varying the laptop brand, which directly impact the compatibility of a smartphone. I vary the laptop brand rather than the smartphone because consumers attending the smartphone market while already owning a laptop, and we want to examine how the valuation of a smartphone changes with compatibility. Two things to notice. First, this is not just a hypothetical question, but we actually ensure that participant report that you're willing to pay for products. We provide them the opportunity to actually purchase a smartphone. And we also provide them the money. The second thing that I clearly do not provide all participants with laptops. I have 1,000 participants, possibly. I introduce a laptop lottery prize which takes place after the experiment, and therefore participant must behave when providing the willingness to pay as if they won the lottery. I said there are many details of this experiment. I'm not going to talk about this now. I'm happy to talk about later if we'll have time. Important part, as I said in the results, that I find that compatibility with laptops increases the willingness to pay for a smartphone by 9% of retail price. And because of that, when I construct the smartphone demand model, I incorporate the compatibility characteristics as part of the smartphone characteristics, which until now. So moving to the structural model. On the demand side, I'm concentrated on the smartphone market. The reason that I'll not talk about the laptop market is because of problem with data. I don't have sufficient data on the laptop market that allow identification. Therefore, in the smartphone market and taking the laptop as given. So I have random coefficients static discrete choice model. This is mainly motivated. So after the experiment, I have a survey and I ask participant, first I examine the thing frequently. I find that consumers attending the smartphone market were already owning the laptop, not attending the market at the same time. Second, I find that consumers are myopic about the future cost of laptops. Okay, so I have indirect utility for consumer I, smartphone J, when owning laptop C. X is the product characteristics that are independent of own laptop C. It's like screen size, memory, and speed. And QJC is the compatibility index that of smartphone J that depend on laptop C. So everything that the functionality of the laptop, of the smartphone that depend on laptops. I have FEM F mixed effect, and as usual, product J unobservable characteristics and consumer product specific term. The beta IK is individual specific taste that is independent of own laptop. And the capital gamma is the part that depends on that. On the supply side, I have FM, which producing a subset of the smartphone. I assume pure strategy, Nash time. Where F maximize profit with respect to P. Now, equation 2 is the one. Is the one that you're familiar in the literature. And the reasons for that, so firms can maximize profit conditional on complementary part because of expected demand due to ownership of a laptop. However, because prices and marginal costs are independent of compatibility, unconditional maximization will provide exactly the same results. Additionally, firm can maximize profit across time within markets, so a dynamic model. However, since I have large product variety, consumer heterogeneity is both via random coefficient and product compatibility, I shy away from the dynamic part of this paper, and I follow Feng and Yin, who analyzing the smartphone assuming static pricing. The last slide, I'll shortly about the dynamic model. Yes, sorry. In the experiment part, I am examining. I'm examining how my results changed with the ownership of laptops. I see that the results are robust. And there are a few reasons for that. One, that consumers actually, the agent actually care about the laptop that we provide them. Let me think about the first part of the question, and I'll respond maybe later or. Okay, so I use GMM to estimate the model where the identification of kappa gamma is by the variation of pre-owned laptop or a given smartphone J. Now, as I said in the beginning, I combined the experiment plot and the structural plot. Uniquely to the IO literature, this has been used in labor literature. I take the experimental results and I combine them with the structural model. Specifically, I take the change in Williams A that I measure in the experiment, and I construct a micro moment with that, so I can pin down the effect of compatibility on the decision of consumers. So down the part. There is a great paper called the Walpin called The Best of Two Words that going over the merging literature of examining structural and experimental models. So moving to the results of the estimation. So I find that the price parameter is 90, which provide me goal value of for additional compatibility characteristics. There is a goal value of $35, which is approximately $10 higher than what I find in the experiment. And there are two explanations for that. So there is a main explanation for that, which is in the structural model, I include more compatibility characteristics, which create a higher variation, Apple, Samsung, the rest, and therefore has a higher value. For the common coefficient, I find that additional has a $15 value, and the elasticity of it is actually half of the mean elasticity is actually half of what Feng and Yang find. There are two explanations for that. First, this is a more mature market, higher screens, and therefore additional inch of screen is worth less. And the second is that compatibility takes part of the power of what actual they previously common coefficient. For Apple fixed effect, I find a substantially lower value than what Feng and Yang find. And this aligned with the story of the paper that it's not just Apple grand fixed effect that matters, but actually part of it belongs to the effect of compatibility. The supply side, I have estimation that align nicely. Okay, so in the last 10 minutes, I'll go over the counterfactual. So First counterfactual is examining how what is the effects of forcing cross-brand compatibility. So assume smartphone J and laptops prime that previously were incompatible are now compatible. I force the compatibility to be the maximum of smartphone J with any other laptop with closed ecosystem, and laptop C prime with any other smartphone with closed ecosystem. So if I own an Apple laptop, Samsung smartphone, now they become compatible, and the compatibility will be the one by Apple because it has a higher compatibility index. So first I examine the annual average effect across spend, where I find that price goes down, consumer surplus is increased. Second, I examine the average film effect across tiers, where we can see that Apple is worse off with open ecosystem, while competitors are better off. Additionally, we see that Apple price drop is the highest, but its contribution to consumer surplus is the lowest. There are two explanations for that. First, that Apple price elasticity is low, and second, that substitution pattern with respect to price change. And examine that, I map the yearly profit by so on the vertical axis, we have the profit difference, and the horizontal axis, we have the years. Apple is in blue and Samsung is in red. What we observe is that Apple is better off in the first 2 years, but it's worse off with open ecosystem the last 4 years. And Apple price drop mainly occurs in the last 4 years, which explain why its consumer surplus is the lowest. Now, the more interesting question is what's going on? Why Apple is first better off, and then it is worse off? To answer that, I plot the smartphone average hardware quality by year. So on the vertical axis, we have the average normalized quality index, which is measured by product characteristics linear combination weighted by the estimated coefficient. On the horizontal axis, we have the years. Again, Apple is in blue and Samsung is in red. What we see here is that in 2018 and 2019, Apple's smartphone quality is much higher than Samsung, but then from 2020 onward, this gap shrinks and remains low. So what happened is that in 2018 and 2019, those who own non-Apple laptop are switching to purchase Apple smartphone because now they can get a higher compatibility, where this results in Apple profit increase and a higher market. However, from 2020 onward, when we have open ecosystem, those who own Apple laptop are switching to purchase Samsung smartphone because they lose no compatibility, and Samsung top smartphone are of better quality. That results in Apple profit drop and a lower market. So if we go back to the question of the effect of open ecosystem on the market, we see that consumer surplus is increasing. And if the regulator is concerned about market concentration, it can condition ecosystem regulation on the quality gap of smartphones between Apple and Samsung. Now, in this counterfactual, I assume that the regulator force the maximum compatibility between a smartphone and a laptop. The interesting question is what's going to be if the regulator force an open ecosystem but allow minimum compatibility between the two products. So if I own an Apple laptop and a Samsung smartphone, I no longer benefit from Apple compatibility, but we take the lower compatibility by Samsung. What I find is that Apple is better off in every period because no Apple laptop owner will switch away to purchase Samsung smartphone because they experience a lower compatibility between products. Finally, I examined the possibility of licensing Apple compatibility, but I find that no such a contract exists because Apple losses are greater than competitive gains. And the reason for that is with closed ecosystem and without licensing, Apple has a monopoly power over Apple laptop owners. When we have licensing of open ecosystem, Apple loses monopoly power, and therefore Apple losses are greater than competitor gains. Quickly going over the cross-market merger between Samsung and HP, which are Apple main competitors in the smartphone laptop market. I allow maximum compatibility between their products, so the same level of Apple. The reason I do that is that we can see that when HP and Motorola merge, their compatibility is exactly the same as Apple. So first result is the average firm effect across years, where we observe that the merged entity Samsung is better off while competitors are worse off. The reason for that is that those who own HP laptop, which I didn't show you, but it has the highest market share in the laptop market, are switching to purchase a Samsung smartphone because they experience a higher compatibility. This results in a lower market concentration, but higher pricing by the merged entity. Because of that, on average, consumer surplus is increasing, but those consumers who have low compatibility value and purchasing from the merged entity are worse off because of the higher prices. Finally, I find that the merged entity is indifferent to compatibility with non-Apple laptop competitors. And the reason for that is that Samsung smartphone quality is high enough to maintain demand regardless of compatibility with non-Apple laptop. So the takeaway from this paper is first, providing a methodology to identify the causal effect of compatibility when we cannot use just market data. Second, we find that compatibility matter even in standalone products, and that open ecosystem regulation and cross-market merger can reduce market concentration and increase consumers' sales. Okay, so I'll just talk about this. So one caveat of this paper is that I assume that firms do not change their product characteristics in response to open ecosystem. However, when we have open ecosystem, firms have lower incentive to introduce compatibility features because now their competitors can use that to attract consumers. In this paper, I examined the effect of open ecosystem on the characteristics decision of firms. I have that in a static model. I need to switch to a dynamic model that show how firms changed their investment decision in response to the ecosystem. Finally, more research is needed on the compatibility of standalone products in other technology market and examining the network effect across products.